This is the 23rd lecture of the course, MTH 204A for section B. Recall that in the last lecture we defined rings and we are talking about some examples of rings. So, we will also continue with that. So, today we will first discuss one of the most important rings, namely the polynomial rings. So, we start with a ring R. So, again let me remind you, by a ring I mean that it has two operations plus an addition and multiplication. With respect to addition, it is an abelian group. With respect to multiplication, it is just associative and having a multiplicative identity, which we also call as the unity, and then we have two distributive properties that connect addition and multiplication. Okay. So, given a ring R by a polynomial, so maybe put it as a definition, by a polynomial in the indeterminate, some authors also call it a variable, in the indeterminate x, a polynomial in the indeterminate x with over or some authors also write with coefficients from R, by a polynomial I mean a finite formal sum of this following: a0 plus a1 x, sum a to an x to the power n, where a0 an all belong to the ring and an of course non-zero. So, this is what we mean by a polynomial over R in this indeterminate x. So, of course, I mean you might raise a very valid objection that what do we mean by this formal sum or this indeterminate. So, the formal definition of a polynomial with coefficients from R is the following, that it is a sequence. I can write here more formally. It is a sequence okay, maybe n union 0. It is a sequence such that whose all but finitely many terms vanish, terms vanish, terms are 0. Okay. So, let me again explain. So, like at least I should tell you that is the connection between them. So, this is the formal definition, that it is a sequence. So, sequence in R. So, it is a sequence of elements from this ring such that beyond a certain stage all the terms will be 0, right. And so, suppose this is what the situation is, that beyond nth terms all these are 0, then we write this we write this sequence by this symbol as well. Okay. So, basically this is nothing but a way of writing this sequence, right. Because you see that I mean x, to begin with, x is not playing any role. The only role that the powers of x are playing is, it is just kind of dictating which ai should sit at which place, right. So, I mean so basically what we are doing is we have a collection of places, and there we are assigning to every place some elements from the ring, and also it has to be that beyond a point everything should be 0. So, with this intuition we can define a polynomial formally by a sequence. That is how the formal we arrive at the formal definition. Okay. So, yeah, as I said that this is nothing but a alternate and helpful. I will tell you why it is why it is useful, a useful way of writing this. I will tell you why this is useful now. So, though polynomials are sequences, special kinds of sequences from elements of sequence with elements from the ring. However, it is customary to overlook or ignore this in our considerations. The main reason is that whenever if we consider sequences, then on the space of sequences, of course we can add and multiply pointwise. So now given so if I take any two sequences of this type, if we add them the way we add sequences, that of course corresponds to usual addition of polynomials, right. Let me again write that. So suppose I am given two polynomials, let us say 0 to some m. Okay. So also I think I should for our convenience, let's change the let's introduce a slightly different notation with a convention, of course, because then it will be easier for us. So whenever a sequence like this, whenever a polynomial is given, we will write that as follows: a k x to the power k, where k is greater or equal to 0. So with this convention that a I is 0 for all but finitely many i's. So what I am saying is, from now on, instead of writing a polynomial strictly from I to 1 up to m, and then we can also write it as follows, that we write it with this together with this. Okay, that's also should be acceptable. And the advantage for this is simply that suppose if this is a polynomial and this is another polynomial, then their sum is simply we can write a k plus b k. The advantage of writing in this way is, otherwise, like if we mention I from 0 to m and then I from another index I from 0 to n, then you see that if m and n are not equal, then this does not make sense beyond a point, right. So then you have to write it, you have to write this part more carefully. But if we accept the custom that given a polynomial we will write it in this form with the understanding that beyond a point all terms are 0. So once we accept this convention, then the addition can be simply written like this. Okay. Now let us come back here. So you see that like the way as I said that if we take two sequences, then pointwise addition, that corresponds to the addition of these two polynomials in the which is very natural, the natural addition of the polynomials. But it is not the same for the multiplication, because again let me remind you, when we have two sequences we can multiply two sequences pointwise, right, like the term wise. But the thing is that that does not correspond to the multiplication of polynomials. The polynomial multiplication is different. That is why, like though formally a polynomial is a sequence, but however since this multiplication is somewhat multiplication indeed different from that of usual multiplication of sequences. So therefore when we are discussing polynomials, we will perhaps not view polynomials as sequences. However, for our purposes enough to regard a polynomial like this or somewhat or this, we will regard them like this, and then it will be easier to motivate how the motivate how the multiplication of polynomials is defined. So there, let me put it. So basically, suppose we have a polynomial ak, and then we have another polynomial, okay. So like for example, let's take small cases, special cases. So let's say 1 plus x square, then 1 plus 2x plus 3x cube. Suppose we want to multiply them, what should be the most natural way? In fact, what we have been encountering since our elementary algebra course in school days. So the idea is that we should first, so if how do we do the multiplication? So if we pick a term from here, another term from here, then we first add the powers of the variable, and then with that we multiply the coefficients. Now, so what happens that in this way we may end up finding several monomials with different coefficients. Now then what we will do is we will club them together, that is we will take the sum of their coefficients. So let me again explain what I am doing here. So for example, here it will be 1 plus 2x plus 3x cube, then we will have x plus 2x square plus 3x to the power 4, and then furthermore we have 2x cube. So 2x cube plus something. The point is that you see that after the multiplication, so for this monomial x we have precisely 2 terms. Now what we will do, we will add their coefficients. So this is how we have learned to multiply polynomials. Now that is exactly how the definition is defined, how the definition is made in the general case over any rings. So how we will do is we will pick up a term here, let us say I, and then pick a term from here xj. So therefore x to the power I plus j, then with that ai bj. Now we would like to take their sum over ij, right. That is how multiplication is defined. Now as I like earlier, by adding up the coefficients of the same monomials, we can put this in this form, that fix something. So give for any given k. So the coefficient of x to the power k is going to be the sum of all I and j such that I plus j equal to k. Okay. So I from 0 to so basically let me put it I plus j equal to k x to the ai bj. Okay. Right. That is how it is defined, and from this definition it is clear that since these two are polynomials, so beyond a certain point, so these coefficients will also vanish, therefore it is also going to be a polynomial. Okay. So that is how the multiplication is defined. Now we now define the polynomial ring. So this is denoted by Rx, is the set of all polynomials in the indeterminate x. So this is just a like in the indeterminate x, this is just more like a custom. Here x is not actually meaning anything. So I mean, as I said, formally these are sequences where you do not need any reference of any indeterminate. So the use of x is being made just to tell you that which coefficient, yeah. So this use of x is here just telling you that which coefficient is to be dealt with what, right. That is exactly the x is telling us, and also I mean writing x, bringing x in the picture, it becomes easier to see the multiplication of polynomials, which would be rather difficult to see from this formal definition. Okay. So, apart from that, x is not actually meaning anything. All right. So this is with respect to the polynomial addition and the multiplication. This forms a ring. Okay. This forms a ring, and it is easy to see that every a in R can naturally be identified with the following constant polynomial a, right. So, this polynomial, okay. So, in that adding to constant polynomials and multiplying to constant polynomials are same as adding and multiplying to elements, the concerned elements from the ring. So, therefore, in that way we can regard that R is a subring of this polynomial ring. Okay. So, let me summarize. So, by a polynomial we mean this, formally this is a sequence, but however we usually do not regard polynomials when we deal with polynomials, we often forget this. The reason, as I said, that bringing x into the picture, that helps us to dictate that which coefficient is sitting at which place. It is basically dictating the places for the coefficients, and with that very rigid control, it becomes easier to see the multiplications of polynomials. Okay. So, this is a ring. Similarly, we can talk about rings. We can talk about polynomial rings in more variables. So, okay. So, like again let me first convey the idea intuitively, which of course going to be useful for us when we of course when we deal with polynomials in several variables, but of course we should also tell you the formal definition. So, to begin with, let us fix variables x1 up to xn. For the time being, bear with me. So, suppose these are variables. So, a polynomial with coefficients from R in these n variables is a formal expression. Of course, we will give the definition, formal expression of this form x to the power I1 xn to the power In I1 I2 In. Okay. Let me directly adopt the analogous convention here. So, it is a sum with these ai1, maybe I should not use too many a's, ai1 I2 In is 0 for all but finitely many tuple I1 up to In. Okay. For example, suppose in two variables, if we fix x and y, then 3x square plus 5xy plus 7x5y plus 8x y to the power 4, this is a polynomial in the variable x and y over, in fact you can take over the ring Z. Okay. So, of course I should tell you the formal definition as well. So, the formal definition of a polynomial in several variables is simply like what was the formal definition when n was 1? So, sequences, right. What is a sequence? It is a map from n to R. So, here it will be a map from n-fold Cartesian product, an n-fold Cartesian product. Okay, maybe I should also include because these are zeros, right. So, maybe what I should do is I should do the following. we take n union singleton 0, n-fold Cartesian product from that R. So, we take a map. So, therefore, a typical element here will look like I1 up to In, where each ai is a non-negative integer. So, its image we will denote this by ai1 up to ain. Okay. So, thus like formally a polynomial in n variables polynomial in n variables it over with coefficients over the ring R is a function from this n-fold Cartesian product to R such that for all but finitely many such tuples the function vanishes everywhere, for all function vanishes for all but finitely many such tuples. Okay. And then you can immediately see that in such cases how to define additions of polynomials. So, that is also clear from like if we add the corresponding functions, because we have already done rings of functions. So, adding them as functions or adding them symbolically you in this manner, like I mean we will just add the coefficients of the same monomial, these two coincide. But again for multiplication, that is for multiplication of course from here it is difficult to have a feeling why the difficult to have a feeling for what is going on. So, for multiplication to visualize the multiplication, it is like what we have to do is we should rather stick to this notation, and like one variable it becomes clear that how multiplications are to be defined. Namely, we take a term from the first one, we take a term from the second one, then first we set up the exponents of the variables, then we also together with that we take the products of the coefficients, and now the product is the sum of all such products, then corresponding to the same monomial we just club together all the coefficients. So, exactly in the same as the one variable case. Okay. So, here the set of all polynomials in this n variables over R, these are that collection is denoted by R x1 up to xn. So, it is a ring with respect to addition and multiplication that we have already defined. Okay. So, thus we have discussed polynomial rings. Next we will talk about power series rings. For simplicity to understand things, let us now stick to one variable case only. If you understand the one variable case completely, then you know that how to extend that to extend that to any general finitely many variables. So, yeah, so as I said that just for the sake of simplicity, let us, and of course convenience in the understanding, let us stick to one variable case from now onwards. So, so now I am going to talk about power series rings. So, that is denoted by this notation R. So, for polynomial it was R square bracket x, now it will be double square bracket x. So, what is a power series with coefficients from R in the indeterminate x or variable x? That is, you can see that the immediate next step of the notion of polynomials. What I mean by is by a polynomial was something such that all but finitely many ak's are 0, but for power series that restriction is no longer there. So, that is by a power series we mean an expression of this form. More formally it is a sequence, and we do not have any restriction that all but finitely many terms of the sequence have to vanish, we do not have the restriction. Okay. So, therefore, you can consider this is just the sequence space, all right. Now, but as I said that I do not we have valid reasons not to I mean not to be quite obsessed with the formal definition, because like in the case of polynomials, so I mean adding to sequences, that corresponds to adding to power series, but for multiplication the scenario is different. So, and in this case the ring which you want to consider is with respect to the multiplication of power series is not as multiplication of sequences. So, therefore, whenever we are talking about power series, we simply forget that they are actually sequences. It is same as polynomial, I mean the story is exactly same as polynomials. So, how, like, let me quickly write. So, the sum is defined as, so as I said that it corresponds to addition of functions, okay, but for multiplications it is like it is defined in the way multiplication of polynomial is defined exactly in that way, but in case, but in like unlike that case, here we might have here I mean we might have non-zero coefficients for infinitely many times. So, as I said that it is of the form I plus j equal to k a I b j x to the power k. Okay. So, that is how it is defined. Then it is like it is a routine verification that everything is associative, like both addition and multiplication is associative. Of course, with respect to addition we do not have to do anything, because for addition it's a group, that part is an abelian group, that part is already taken care of when we talk about general rings of functions, right. So, like again what I mean is let me again, so consider x to be n union this. So, by a power series is a function from x to r. So, in this function space the addition of functions is pointwise, and that exactly corresponds to addition in this power series ring. So, since we have done this in generality, so we do not have to do anything here with respect to addition. For multiplication it is easy verification, routine verification that this is associative, exactly same as the way we do for polynomials, and thus this with respect to this addition and multiplication this forms a ring. Okay. So, several interesting things happen in the power series ring which are not present in the polynomial ring. We will talk about them later. Maybe I can just mention one or two. Before that, let me remind you, for a given polynomial, let us say a polynomial like this. Okay, so, the custom is that if beyond this point all coefficients are 0, if some coefficient is 0 we can simply ignore that term while writing. So, like the largest non-zero, largest n for which the coefficient is non-zero, that is called the degree of the polynomial. Then of course, if this is degree is defined for non-zero polynomials, and then we have usual formulas which are easy to verify that this is maximum of degree f and g. Okay, this is the maximum of degree f and g, and similarly we have I mean we can talk about degree of their product. All these things can be done. Here it is very tempting to write down that this is the degree of a plus degree of g, but it is certainly not the case, because like the leading terms their product might be 0 in an arbitrary ring. So, these things are there for, but for power series we do not have any notion of degree for natural reasons. Now, the thing is let me just leave it as an exercise. So, let us say you consider zx. So, question is what are the units. So, by a unit I mean an element which is having both sided inverse, right. What are the units in this ring? Okay. You see that sorry, maybe yes, yeah. Let us directly ask this, instead of Z, let us take Q or R. What are the units? You see that the units will be only the constant, non-zero constant polynomials, but however, for power series the situation is different. I also would like to leave it to you as an exercise that in the power series ring, E is an unit if and only if A0 is an unit, if and only if this is an unit. Okay. All right. Okay. So, this you can I am leaving to you as an exercise. This is a simple exercise. So, now you should move from power series to LoRa series. So, let me first define what I mean by a LoRa polynomial. LoRa polynomial. So, LoRa polynomial is a polynomial except there could be finitely many terms, finitely many monomials where the power of finitely many monomials with negative powers of x. So, what I mean by this is the following. Let me just write an example, then I will write down the precise definition. So, it is basically like this. Let us say 5x to the power 5, 2x to the power 4, then 3 by x plus now then some polynomial that 5 plus 2x plus 7x5, something like this. So, like the definition is that it is a formal expression such that, like as usual all but finitely many terms vanish. Remember, both the positive and negative side we can have at most finitely many times, finitely many terms, right. So, with in addition to a polynomial, only the only thing we allow is the presence of finitely many negative powers of x, okay, finitely many terms with negative powers of x. And the formal definition should be as follows, that it is a sequence from Z to R means the ring R, which we have assumed in the beginning. This is all functions from Z to R with all coefficients, all but finitely many coefficients are vanishing, okay. But again, as I said that though it is formally a sequence, we will often forget that and rather write a LoRa series like this, okay, LoRa polynomial like this. And how the addition of two LoRa polynomials are defined is exactly in the usual way, that we should add them coefficient wise, and then the multiplication is also defined in the exactly similar way, that is we take one monomial from one, another some other or one monomial from the one, another monomial from the second. We will first add their powers of x. Remember, here it could be negative, and then with that we multiply the coefficients, okay, and then corresponding to the same monomial we club together all the coefficients. So, it is done in the very usual way, and I leave this to you to check that this indeed forms a ring with respect to this addition and multiplication. So, that is called the ring of LoRa polynomials, and remember that from polynomials to like we start with polynomials, then from that we went to power series. So, now from Laurent polynomials we will be leading towards Laurent series. Okay. So, in all this setup, the ring that we have chosen, that all these can be defined over any ring, but more often than not we consider the ring to be commutative, because when ring is commutative we can do some more interesting stuff there. But yeah, it can be defined over any general ring, but as I said, usually we consider the ring to be commutative, because when the ring is commutative we have better ways to deal with that. Okay. Now let us talk about Laurent series. Again, Laurent series is exactly same as that of power series, except we should allow finitely many terms with negative powers of x to appear. So, basically it is something of this form. Such that for all but finitely many negative integers k, ak has to be 0. So, basically in a Laurent series you are allowed to have only finitely many negative powers of x, but for the positive side we do not have any restriction. So, let me give you an example. An example for this would be, let us say the following: x square 1 by x plus 1, then ax plus x square is going like this. So, this is a Laurent series. Okay. And by now you must have already realized that like in the previous manner we can talk about the addition of two Laurent series, and then of course we can multiply two Laurent series. Okay. We can add two Laurent series, we can multiply two Laurent series. The multiplication is, again, you should not confuse the multiplication of Laurent series with that of sequences. That of sequences, and that of sequences which formally that object that a Laurent series is. So, for the purpose of discussing Laurent series, we will, like earlier, we will simply ignore that it is actually some sequence. Rather we should stick to we will treat them as expressions with these restrictions. Okay. All right. So, this Laurent series ring, this is denoted as R double bracket x, double round bracket x. So, with respect to the usual the addition, natural addition and natural multiplication, this forms a ring. Okay. And of course, you might ask that do we have any such do we have any analogues here? So, you can immediately see that this power, we do have these inclusions. R is contained inside its power series. Okay. R is contained inside its polynomial ring. It says R is a subring of its polynomial ring, and this is further a subring of power series ring. Okay. On a different side, R is contained inside the ring of Laurent series, for which right now I am not assigning any notation, and this is contained inside ring of Laurent series, and this also contains the power series ring. Okay. So, contains the power series ring. So, the analog of this in this setup would be the following, that is, every non-zero Laurent series will be unit. Every non-zero element in this is an unit. Okay. All right. I should now move to other examples. Next example we will talk about is complexification of a ring. So, the reason for calling this complexification is you see that it exactly generalizes the procedure of constructing C, that is the set of, that is the field of complex numbers, from that of real numbers. Okay. So, recall that like C can be defined in this way, that we can define C in this way, that it is a collection of, it is R2, the collection of all pairs of real numbers. Addition is defined component wise, but the multiplication is defined in a slightly different way, AC minus BD, AD plus BC. Okay. That is how we can define. So, the same procedure can be the same procedure can be applied for any ring R. R is any ring. So, what are we doing? We consider R cross R. So, we denote this by RC. The C means this complexification. So, what this is nothing but the twofold Cartesian product of R, and we define exactly in this way. AB, CD, AC minus BD, AC minus BD, AD plus BC. You can immediately check that with respect to these two, with respect to this addition and multiplication, this forms a ring. This is called the complexification of R. So, for example, so like you can complexify Z, then what will you, okay. So, here also you should make another observation, that with respect to this multiplication. So, let us start from here. So, here this pair 0 comma 1. So, in this R cross R, this collection x comma 0, x belongs to R. This is you can see, so this is identified with the real number x. So, that is this in fact this turns out to be a subring of C. So, this subring is naturally identified, or more formally it is isomorphic. Of course, I will define the meaning of isomorphism between rings, but for the time being just bear with me. So, this is you can convince yourselves that it is naturally identified with that of R. So, therefore, thus R can be considered as a subring of C, and this element 0 comma 1, its square becomes minus 1 comma 0, which I again said that is simply identified as minus 1. So, this is what this is what we set as I. Okay. The same, you can see the same observation goes here as well. So, so there is a copy of R contained inside this complexification, namely all having the second component 0, and 0 comma 1 is simply becoming, yeah. So, this it is a square root of the unity. Okay. So, let me give you a few examples of complexifications. So, if we start with Z, what are we supposed to get after complexifying that? Okay. So, I leave it to just convince yourself that this looks like Zi. So, this looks like these things. I am just for the timing I am being quite yeah. So, for the time being I would like to be vague, and I would like to leave you, I would like to leave it to you to convince yourselves that like this complexification of Z, that exactly looks like Zi. Similarly, you can do with Q. What you should obtain is it looks similar to Qi. Then R, of course, we expect that the complexification of R will be C, because that is how it is defined. Then also you should do for z root d, where d is a square of integer. So, basically the rings that we have seen in the previous lecture, just to you can simply consider their complexifications, and then you can try to see whether after complexifying the rings, whether you are whether you can recognize these new rings exactly similar to some ring which is already familiar to you. Okay, so this is complexification. I won't talk about that more here. Now I will move to some another example which is called group ring, and with that perhaps I will end this discussion on the examples. If you pick up any textbook in algebra, you may find other examples as well, because like it's very difficult to produce a finite a finite and complete list of examples. But however, the main and the common examples I have talked about. Now let us talk about group ring. So let us begin with a finite group. If it is infinite, then we should we will see what to do. Let us start with a finite group and R a ring. What we are going to do is we are going to show that given a group and a ring, we can from these two things we can construct a bigger ring which contains which contains G as the subgroup as the yeah. So okay, I will do that, and we will see that we are going to talk about construct something called group ring RG. Group ring RG. So what is RG? RG is first of all, to be formally, it's all functions from G to C. Okay, all functions from G to C. Since G is finite, we will have another useful way to represent a function. So so given a function in RG, okay, so we will write f as fg times, so ft times g. So this is a formal notation for writing like this. So what we are doing is, corresponding to every point, we are considering the value of the function at that point. Now we simply write that value. So sorry yeah, so which is a ring, which is from the ring, the value formally dot g, and then we take their sum. So thus if I write a group element, if I write this from that, if I write an element of this collection by this, that means I am considering the function which is taking the value ag at the given point g. Okay. So let Rg be the collection of all such functions. Okay. Now we want to talk about the addition of such functions. So the addition is exactly same as the addition of two functions pointwise, or in this notation, like you see that in case of polynomials also this kind of notations becomes it makes our life easier to understand what is easier to see how things are being done. So in this notation, if we write down the addition AGG and BGG, what we obtain is AG plus BG. Okay. So basically, corresponding to every group element G, we add their coefficients, and this makes sense because we are dealing with a finite group. Now we have to talk about its multiplications. So it is convenient to convenient to define the multiplications symbolically using this notation. Then of course I will tell you what at the level of functions it is defined. So first let me do it symbolically. So again recall that given a function, given a member from this collection, it is uniquely written it's yeah. So for given any member in this collection, there exists a unique set of AGs such that this can be, the function is written like this, okay, because this AG is going to be the value of the function at the point G. So therefore, if we take two functions, two members in RG for let me use different in dummy variables BH, H. So the product is defined in this way, G in G, H in H. So it's exactly same as you see polynomials. So AG, BH, then GH, okay. There is a way to put that neatly, like the way we write down the way we have put the multiplication of two polynomials in a much more neater form, that also we can do here. That is, we might, so corresponding to every group element x, we will write down the coefficient of x. So what is that? So this is where I am going to write down the coefficient of x. So therefore the coefficient of x is basically sum of all such things AG times BH such that G times H is x. So therefore GH is x, AG, BH, okay. Of course you can also put this in the following form. In fact, as I said that it's easier to define the multiplication in this multiplication purely symbolically by using this notation. Then we can immediately see how it is to be defined formally as functions. So here you can write it like this. So GH is x, right? GH is x. So therefore H is G inverse x. Okay, yes. So H is G inverse x. So H is G inverse x, fine, or maybe I should write it as G is equal to x H inverse. Yeah, maybe that's a better way. Let's see, it's all are fine. So here it will be so B, H is x, so G is x H inverse, so AX H inverse, BH x, yeah, that's a better way. So now we have only one, so yeah, so H belongs to G, or maybe I should change the variable by x and y. X y inverse by y in G, okay. So that's how the product of two elements in here it is defined. I leave this to you to check that this with respect to this product, and of course the addition, like for addition you do not have to prove anything, because that already for any set and any ring this form we have checked that with respect to pointers addition it is an abelian group. So for addition you do not have to do anything here, but for this new product you have to check that it is associative and it has the rest of the required properties. So so then RG with respect to addition and this product, maybe I should denote this product, though it is done symbolically, like symbolically it is very natural to define the product like this. Let me denote this by star, this is convention to denote this by star. RG, this star is called the group ring, okay. So it is a group ring, So, given a ring and a group, I can form a group ring. Okay. So, I forgot to tell you that how this looks in terms of functions, that is suppose this is the function f and this is the function f1, this is the function f2, then what should be f1 star f2, because all these are functions after all, right. So, this is also a function. So, if I want to write this as a function, then so the definition is this is simply y in y f1 x y inverse f2 y, okay. That is how it is defined. This star is called the convolution called the convolution, and of course you should immediately understand that this product is defined from the pointwise product of functions. So, therefore, this ring is not exactly same of the rings of functions, okay, because while defining rings of functions we are not using any structure on the ground set X. In this situation the ground set X is a group. So, in the multiplication of the group is the multiplication of this ring is defined using the multiplication of the group, okay. Now, since I am almost towards the end of this lecture, I should say a few more things, then with that I will finish. So, yeah, so given a group, to begin with, we have taken finite group and a ring. We can consider this, which is called the group ring of the group G with coefficients from R, okay. Yeah. So, in these considerations you see that like this notation made sense because it is actually a finite sum. So, because the group is finite, so it is natural to ask that what happens if the group is infinite. So, if the group is not necessarily finite, then of course we consider functions, but not all functions. We should consider those functions which vanishes at all but finitely many points. So, the general definition of a group ring for any group G, Rg is basically the collection of all functions f vanishes at all but finitely many points of G, okay. So, this is the collection we are going to consider. So, as usual, the defining addition is not an issue because it can be defined for any two functions. So, if we convert that to here also you can represent f by this notation AG G, but we have to mention that all but finitely many AGs are 0. So, now if we, as I said, it is customary to whenever we are talking about this Rg, we should write the elements by the such symbols. So, therefore, if we want to see that how the addition of two functions look in the if they are written using the symbol, then you see that like that of finite case, we are just adding the coefficients corresponding to every group element G. And similarly, we can also do this. Remember that since in this all but finitely many AGs and BHs vanish, so therefore, here also for all but finitely many x, this terms finitely many x, this is going to vanish, okay. So, therefore, if we want to do the product in this manner, that makes sense. And in terms of function, this should look like this, okay. So, this looks like this, and here also you can see that in f and g are finitely supported, as beyond a finite set they vanish, then of course this is also going to vanish for all but finitely many x, okay. So, in general, like the finite case, Rg is also a group with also a ring with respect to the addition and the star and the convolution, Okay, so a few more words. So inside Rg you can see that Rg, this group ring, contains R as a subring. How? I should justify what this means. So consider the following: this group has an identity, right? So therefore we can talk about these functions which are taking. So A is okay. So this is, you can see that naturally, of course formally it means isomorphism, homomorphisms and isomorphisms I will define in the next lecture, but before that you should feel, I mean you should convince yourselves that this ring and R, they are same, because the sense of isomorphism is already familiar too. Adding two things here is same as adding two members in R. So this is a subring of Rg, which is similar to R. Okay. So this contains R as a subring, and its group of so given a ring R, R star is the group, I mean it is the collection of all its invertible elements, its unit, it's all units, and that is, you can immediately see that it forms a group, okay, because apart from invertibility all the necessary things are already present. So yeah, so this is called the unit group of any ring. Now the unit group of this very particular ring that contains G as a subgroup, okay. So how this is this, each G, so will consider like this collections. You can easily see that this is isomorphic to a subgroup of this isomorphic to a subgroup of its group of unities. So therefore this group ring in a sense both contains R as a ring, R as a subring, and its the multiplicative group contains Z as a subgroup. Okay. So I am almost done. And just to make one or two more remarks, that so here also you see the sums are finite sums, because the functions are finishing at all but finitely many things. So in analysis, when you will do Fourier analysis, you will or even advanced stuff, then also you will encounter this word convolution, but that is a difference. I mean that is defined with some more more technicalities, but however you will be able to see the exact similarities. So there some will be replaced by integrals, and of course then in order to talk about integrals you have to talk about a coherent measure. So these things we will see in the analysis, but I am getting to that. So okay, with that I will finish this lecture.